Welcome to College Algebra. We're going to take a look at section 3.1 from our textbook. We'll actually be covering probably the first three sections, I think, in this video series just for my face-to-face students. But let's talk a little bit about Chapter 3. Chapter 3 is where we introduce functions in this class, and functions are a really important topic in college algebra. Depending upon the instructor, sometimes it's one of the first topics we really talk about in the course, and the whole semester is framed through that subject. In this case, we introduce it in the second unit, and it's going to stay with us really through the rest of the semester. A lot of the rest of the chapters and sections will be focused on looking at functions from a slightly different perspective than we do here when we start out. So let's talk about functions. First off, let's have a definition. So here's the definition of a function. A function is a correspondence or relation between two sets, a set of inputs called the domain of the function, and a set of outputs called the range of the function, such that each input has only one output. Now, a relation or a correspondence is just any relationship between the inputs and outputs. But a function adds the condition that each input only goes to one output. So, for example, suppose 2 was the input and 7 was its output. No matter how many times you plug in 2 as the input, you get 7 as the output in a function. Whereas just in a generic relation, you might plug in 2 multiple times and get different numbers each time you plug it in. A function has a consistent behavior, whereas a relation not necessarily. There are a lot of different ways of expressing functions. We will look at functions that can be expressed as equations. We'll look at functions that can be expressed as points. But generally, a good way to start out is to start out with arrow diagram problems, which is a very simple way of expressing a function. So we're going to look at an example from our textbook. Alright, we're going to look at exercise 19 here. So here is a function. We have a set of inputs, we have a set of outputs, and we want to talk about whether this is a function or not. So it's very simple to tell that. You just look at each input. How many outputs does it have? Elvis has January 8th as its output, as his output probably. Colleen has January 8th as well. Kaylee has March 15th. Marissa has September 17th. Each input only has one output coming out of it. Now, this output actually has multiple inputs going into it, but that's not the condition for a function. Remember, the condition for a function is each input has a single output. It doesn't really say anything about how many inputs a output might have. So yeah, you just look at the input side, see how many outputs are coming out. If it's more than one, it's not a function. And just in general, this idea of birthday would generally be a function, even without specifying the specific domain. Because if you think about birthday as a function, well, whatever person you put in as an input generally only has one birthday. I think you'd have to construct a very special kind of case to come up with a person who has 2 birthdays. Here in 21, well, you can examine whether this is a function or not, but it is not because 20 hours actually has 2 outputs. It goes to 200 and 300. You can probably figure out whether 20 and 22 are functions or not as well. 22 is, 20 is not, because Bob has 2 outputs. John and Chuck both have 1, but because Bob has 2 outputs, the whole thing is not a function. And 22, you can see here, each input has 1 output, so it's a function. These problems also ask us to state what the domain and range are. Well, if you look at this, the domain would be all these persons, so Elvis, Colleen, Kaylee, and Marissa. That range would be the birthdays. So yeah, you could easily express functions as points as well. You can see in these problems that we have input values, we have output values. So it's relatively simple to determine whether you have a function or not. Here we've got 2 as an input, 6 as an output, -3 as an input, 6 as an output, 4 as an input, 9 as an output, 2 as an input, 10 as an output. Generally, the x-coordinate, or really when we get into equations, x is generally denoted as the domain variable, whereas y is the range variable. They also have specific titles we'll get into here in a second. But is 23 a function? Well, if you look at it, do any of the inputs have multiple outputs? Well, 2 does. 2 goes to 6, and 2 goes to 10. Because of that, not a function. Whereas 24 is, because each input we have, -2, -1, 3, and 4, each only have one output with them. You can scan down to see if you can find any more that aren't functions. This one looks fine. This one, -2, goes to both 4 and 6, so that's not a function. 28's not a function because -4 goes to 4 and 0. 30 looks fine. 29 looks fine. So 29 and 30 are both functions as well. So yeah. It's honestly a pretty easy process to tell from this kind of format whether you have a function or not. It's a little bit harder when you start getting into equations. Functions can definitely be written as equations, especially if their inputs and outputs are both numbers. So let's take a really simple arrow diagram. Suppose we had as our domain set 1, 2, 3, and 4. And we had as our range 2, 4, 6, and 8. Well, we could have a very simple function just doing this. We could also express what this function does very easily through an equation, because if these are our outputs and these are our inputs, well, we can just think of, okay, 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. How do we get from here to here? Well, we're just doubling the x values. So if you think about y is just double x, that would be y is 2x. And that would be a function. Y is the output, x is the input. We would actually call this a function of x, because x is the domain variable. When we have an equation that represents a function, we will often call that a function of whatever the input variable is. And we'll also say, for example, that this variable y, the output, is a function of whatever the input variable is. So let's actually get a little bit more terminology before we go much further. We have independent variable. The independent variable is the domain or input variable in an equation. That's a function. So these are all 3 names for the same thing: independent variable, domain variable, or input variable. That is usually x. Sometimes we'll use a different variable. In that case, we will definitely indicate what the independent variable is, but it's usually x. Then, dependent variable, you might guess, is the range or output variable. So that's usually going to be y. We'll actually have a notation for functions later that specifically indicates what the input variable is, since that's pretty important in a given function. Let's look at some equations. We already talked about y equal 2x and indicated that was a function. These problems asked us to determine whether the equation defines y as a function of x. So let's look at, say, y equal x cubed. If you think about that, y equal x cubed, let's try a point table. A little lopsided here. So if I plug in 0, I get 0. If I plug in 1, I get 1. If I plug in 2, I get 8. And no matter how many times I plug these in as inputs, 0, 1, or 2, I always get the same value. 0, 0, I'll get 1, 1, I'll get 2, 8. And if I plug in -1, I get -1. But if I look at, say, this one, x equal y squared. Well, let's solve that for y. So I've got x equal y squared. If I square root both sides, I will get y, just switching the sides left to right, equals plus or minus. Don't forget, when you take a square root of both sides of an equation, you do have a plus or minus, the square root of x. Now, because of this plus or minus, we're going to have a different result this time. Because now, when I plug in 1, I will get 1, but I also could get -1 because of the plus or minus. You know, if I plug in, say, 4, I could get 2, or I could also get -2. Really, the only number I could plug in here that I wouldn't get 2 answers for would be 0, just because I would get plus or minus 0, and plus or minus 0 is equal 0. Plus 0 is the same thing as minus 0. So because of that, 0 is the only one that actually only has a single output for a given input. But every other input, 2 outputs. So that means 37, not a function. Really, anything where you solve for y and you get a plus or minus would not be a function. For example, if you solve 41 for y, you will get a plus or minus, so that's not a function either. Same thing for 38, 42, 36, you can already tell is not a function. I guess that's one of the ways you can tell whether you have a function or not, when after you solve for y, you get a plus or minus. That's certainly not the only indicator that something is not a function, but it's probably one of the only indicators we'll see, just because you have to start getting into much more complicated definitions of functions as equations before you start getting to other types of situations that would make an equation not a function. So look at those, test out whether you can tell which ones are functions or not. When you're done with that, let's go back and look at some notation now. We're now going to introduce the general notation when you have an equation that is a function. So if an equation defines y as a function of x, we denote this by replacing y. So we're just going to remove y and replace it with a notation of this form: f parentheses x parentheses. Let's break down this notation a bit. F is just the name of the function. We will see functions that have different names than f. For example, we've already seen that function y equals 2x. Well, we could have just as easily called that g of x. Or we spoiled something later. Equals 2x. Or we saw that x cubed was a function. Y equal x cubed. We could have just as well called that function s. S of x equals x cubed. So this notation is just a replacement for y. That's all it is. It's really just a way of indicating, one, that this is a function, because not all equations are functions. We just saw that. And it also has some other helpful aspects to the notation as well. The unfortunate part about it is that it also looks similar to something we've already seen before as well. Let me actually go down here. It looks like a multiplication, but it is not. The g and the x are not multiplied, they're just written next to each other because they are inseparable. They are of one piece, because it's just a replacement for y, and you wouldn't split up y into one part of its symbol and another part of its symbol. It's an indivisible unit. The same thing with g of x and s of x and f of x. Parentheses indicate what the domain variable is, and it doesn't have to be x. It's just x a lot. Sometimes it's t, sometimes it's w, it even could be y. It just, whatever is in that parentheses indicates what the domain variable, the independent variable, is. And the pronunciation, which I've already spoiled several times by how I've been referring to these, it's hard to get out of the habit. Pronounced f of x, or g of x, or s of x, the name of the function, and then what the independent variable is. So if I had, say, a t in here, it would be g of t. One of the nicest things about the notation is that it makes finding points really easy, because, for example, if we had this formula, y equal x over x squared plus 1, in previous sections, if we wanted to find points, we'd have to say, like, x equals 0, and then we would plug that in and get a y value that goes with it, which actually will come out to be y equals 0. Well, one of the nice things about this notation is that it makes for a very concise way of writing what you've done to find a value, whereas this one, you have to know what x value you plugged in to get this y value. This notation really tells you, because we know f of x, this is actually problem 45 from the text, f of x equals x over x squared plus 1. Well, the first thing we're asked to find in this problem is find f of 0. Well, if you'll notice, x has been replaced by 0, so the work just comes down to putting 0 where x was in the formula. So 0 squared plus 1. Of course, that's going to be 0 over 1, so that's just 0. And if I plug in 1, that's 1 over 1 squared plus 1. That's just 1/2. Negative 1. Well, that's very similar. The top will be negative 1. The bottom will be negative 1 squared plus 1. And that's just going to be negative 1 over 2. F of negative x, you might be able to make a guess of what this is going to be from looking at the previous one, but let's see. So f of negative x, you would plug in negative x for x, so negative x over negative x squared plus 1. On the top, that'll still be negative x. On the bottom, that'll be negative x squared, so negative x times negative x is x squared plus 1. Notice all that is just the opposite sign. One opposite sign on the original function. So when we got 1/2 from plugging in positive 1, when we plugged in negative 1, we just got negative 1/2. So that's the way this function works. That's not always going to be true, but this function works that way. You might be wondering how to do this one, negative f of x. That negative is just a multiplication by a negative, so it's literally a negative in front of the function. Which, by the way, is the exact same thing as this one. In this case, f of negative x is equal negative f of x. This actually means it's called an odd function, which we'll define, I think, in the third section, 3.3. But this is just an example of a function that does happen to be odd. Anyway, f of x plus 1, plug in x plus 1 for x. Alright, plus 1. There we go. This one we can simplify a little bit, because the bottom has some like terms after we multiply out. X squared plus 2x plus 1 plus 1. Don't forget, when you square, exponents do not distribute, so you are going to have to FOIL out x times x, x times 1, 1 times x, 1 times 1. And on the top isn't going to change at all. Honestly, I can just ignore that for a while, but we'll keep it in there. X plus 1 over, and I can combine my two 1s on the bottom, so I'll have x squared plus 2x plus 2. And there we go. F of 2x, well, that would give me 2x over 2x squared plus 1. Oh, plus didn't really come through there. All right, that would equal 2x over square 2 squared x, so 4x squared plus 1. All right. And for our last one, sorry, I had to get rid of my notation there. For our last one, plug in x plus h for x plus h over x plus h squared plus 1. Honestly, this one, you could probably just leave in this form. If I multiply it out, I'll show you what I get, but you can't really simplify anything after it. You can't really combine any like terms, so it's not really worth it. X squared plus 2hx plus h squared plus 1. Don't forget to FOIL out. So yeah, since I can't combine the h squared and the 1, there's not a whole lot of point in doing that work. Alright, I think that'll be it for our part 1 of 3.1. We'll finish out in a part 2 video. I think 3.2 and 3.3 may each be a single video though. It's just 3.1, we introduced so much stuff, I thought it would be best to break it up into 2. As always, have a great day. We'll do the next video.